All right, everyone, welcome to Rook, which is storage for Kubernetes. My name is Blaine Gardner. I work for IBM and Red Hat in our storage division.
Hello, my name is Benamar Mekhissi. I work for IBM, Data Foundation team, the storage team, actually.
All right, I'll start off with a brief agenda. So the first part of the presentation is going to be an introduction to Rook and Ceph. Some of you may have seen some of this before. I also want to talk about new features that we have in our latest release and some things that we're looking forward to in our next release and possibly beyond. I'll also make a note, I like to have slides that are a little extra full. So this PDF will be available on the Sched link afterwards. If something goes pretty quickly, you'll have a chance to get it afterwards. I'm also really excited for Benamar to talk about application disaster recovery, including Rook, so let's get started. As for an introduction, Rook fundamentally is Ceph storage orchestrated within Kubernetes. So Rook allows deploying and managing Ceph with custom resources and automates deployment, configuration, and upgrades of Ceph. And the goal is to allow you to consume Ceph storage the same way you would consume any other storage on Kubernetes with persistent volumes and persistent volume claims. And importantly, Rook is fully open source, Apache 2.0 licensed. Ceph is a fairly old storage solution. If you want to know more about Ceph itself, you can go to ceph.io. Ceph is really important for Rook because it provides us with the three main types and protocols of storage. We have block storage, if you want RWO. We also have a shared file system if you need multiple pods to share the same file storage. And we have S3 protocol object storage as well. So when Rook began, I guess I'll start with the last bullet. Fundamentally, we wanted to avoid the growing pains that come with developing a brand new storage engine from scratch. So we sought out and finally decided upon Ceph. Ceph is fully open source and it has a great community. It's also designed for scalability. Ceph clusters scale to hundreds of nodes and thousands of disks, up to petabytes and possibly beyond at this point. It also has a proven history of enterprise adoption. One of the big and exciting users of Ceph is CERN, that is among the bigger Ceph clusters in the world. And Ceph has been around since 2012. Importantly, Ceph has strong data durability. It's designed to be consistent, not eventually consistent. When Ceph says that your data is written, it is actually written, and it is actually persisted. Your Ceph data is sharded across availability zones, and commonly we see racks, nodes, and disks being in the tree of deciding how things are sharded. Replication is by default, but Ceph also supports erasure coding in recent years, which is really common for object storage, especially sort of cold storage scenarios. And even in extreme disasters, really extreme disasters, we've been able to recover data from Ceph clusters manually. We often get asked about the architectural layers. So Rook really is only deploying and managing Ceph. It doesn't sit in the I/O path. CSI similarly can provision and mount storage, but it also isn't in the I/O path. Ceph is the data layer, and your applications through those mounts talk directly to Ceph. We strive to make Rook as easy to install as possible. We have Helm charts and we have manifests that cover examples for a lot of configurations. And if you're interested in more, Rook's website is rook.io. We have a Get Started link that you can click on. We also strive to make sure Rook can run anywhere Kubernetes runs. This can be in the cloud or on premises. Your hardware can be bare metal or virtual machines. And that underlying storage can be just disks attached to nodes, and it can also be cloud volumes. And for just testing scenarios, we also support loopback devices. One of the questions that often comes from this is why would you deploy Rook in the cloud? And this is something I'm also pretty interested in, and some of the reasons that we see our users say is some clouds just have limitations. Your storage may not be available across availability zones, or you may be too limited on the number of PVs that you can have per node, or if you really only need small PVs, your performance may be limited. And so beyond these, Rook can also just allow consistency across clouds, or if you want to include on-prem as well. As far as storage configurations, generally the default configuration that we talk about is converged, where Rook is running and your applications are right there running alongside Rook. The next step a lot of users take is to have nodes set aside for storage, and this is also supported. Node affinities and taints and tolerations support this pretty easily. The third is having an external Ceph cluster, which I'll dig into a little bit more. A lot of times we've been calling this a provider-consumer architecture, and we support one or more Kubernetes clusters with Rook consuming a central Ceph cluster, which could also be a Rook cluster. This configuration, depending on what your needs are, can support isolating tenants in a multi-tenant scenario, and applications can be migrated from one Kubernetes cluster to another and still have access to the same storage without having to actually migrate that. CSI driver is very functional. The core things here are thin provisioning and topology awareness, as well as snapshot support. Our CSI team has also done a lot of work with some add-on non-official CSI to support things like encryption keys and space reclamation, some things that are a little more unique for Ceph itself. Rook also was one of the early projects to kind of dive into provisioning object storage buckets, S3 for Rook specifically, using a pattern that's similar to how you would claim a PVC, but instead of mounting it to a pod, you get a secret, and then you can get the connection credentials from that secret. And this is also something we're continuing to invest in with the Container Object Storage Interface COSI project. We also get asked a lot about cluster maintenance. Day 2 operations are just a given for storage. So all of your nodes in one failure domain can be down, and there's no Ceph cluster outage. We also try to manage pod disruption budgets, and these help that if something is down, Rook isn't going to be attempting to take something else down as well. And the Rook upgrades try to make sure Rook coordinates with Ceph when doing upgrades to make sure that when it's doing them, there isn't going to be cluster downtime. And generally speaking, your data is safe as long as one of your failure domains comes back online in a disaster. And that's not even with having to do manual steps to get access to that data again. We also have a kubectl plugin. A lot of day 2 management and troubleshooting just doesn't fit into the typical desired state patterns that Kubernetes users typically expect. So we have a kubectl add-on that helps with some of that. There's a link at the bottom if you want to see more, or if you have things that you want to see automated. As for the Rook project itself, community is very important to us. We have a monthly community meeting, which is the second Tuesday of the month at noon Eastern time, which happens to be this exact time slot. So yeah, next month, if you want to come to the Rook community meeting, say hi, get more information, please do so. We also have 4 companies that are primary contributors. We have Clyso, Cybosu, I'm with IBM, Red Hat, we're with IBM, and Upbound has 2 of the founders of the Rook project as well. I checked last night, and Rook has over 500, approaching like 550 contributors on GitHub. We are a graduated project. We graduated 5 years ago this month. It is October? No, it's November, last month. And really core to Rook from the beginning was stability. We declared stable 6 years ago. We have, I couldn't attempt to like count the upstream users running in production, and we do have thousands of downstream production deployments that all rely on Rook. And I really like talking to users about Rook. We've had users say that they're running NVMe disks and InfiniBand networking, and like they're really pushing performance. And we've had users say, yeah, I installed this on 100 USB drives on some spare desktops. So it's just really cool to see the wide gamut of where people are using Rook. We release about every 4 months. 1.18 was in August. We'll have a release coming up next month in December, probably early in the month. And we release bi-weekly unless there's a more critical need, in which case we'll release ad hoc. The project updates. In 1.18, we have now stable and default integration with Ceph CSI's new operator. We also have some keyring rotation for CephX keys, and CephX keys are pretty nitty-gritty details, but it's what Ceph uses to authenticate internally within itself. We have some optimizations for Mon failover to help that happen more quickly. Mons are vaguely equivalent to like etcd in the Kubernetes space. And then just some quality of life improvements for multi-tenancy and some validation validation to help make sure that you're setting up node topology correctly. Looking into the future, something we've been trying to kind of work out for a while is replacing OSDs that share a metadata device. And this is something we're really hoping to get in for 1.19. And also looking into, for the bigger users of Rook that have multiple clusters, being able to parallelize some of the Ceph cluster reconciliation. We're also slowly going to be phasing out the legacy CSI controller. And we're also looking to integrate with Ceph's new NVMe over Fabric support. And yeah, working closely with the Ceph team to make that a reality. We're also going to be integrating with Cozy's V1 Alpha 2 release that's coming up soon. And yeah, now I'm excited to pass off to Benamar.
Hi again. So we'll talk about application disaster recovery. And first I will, in the next few slides, I will talk about how Rook and Ceph actually contribute to the setting up disaster recovery at the volume level, and then we finish it up with to show actually the application disaster recovery, how all of that fits together. So disaster recovery, in a nutshell, it is the ability to restore your critical applications when disaster hits. Every organization needs to have a plan to recover from a disaster. So you might ask the question, doesn't Kubernetes provide high availability, right? And yeah, somewhat. I mean, it does provide high availability for pod, for example, right? Nodes, right? If a pod fails, Kubernetes is going to restart the pod. If a node fails, Kubernetes is going to start all the pods that were running in that node somewhere else, surviving nodes. And then also resource issues, like if a pod is consuming, if a node requires more memory, for example, if pod requires more memory, so low quality, low priority pods are evicted and restarted in another node. But Kubernetes itself doesn't help you when the entire cluster fails. Data corruption, right? And then storage backend failure, right? In that case, there is nothing you can do about it. You have the application running in the Kubernetes cluster, but it cannot access the storage. So that's a disaster, right? And you need to recover from it. And then a cyber attack, that's also something that Kubernetes does not help in that space. So it's all about business continuity, and there are two key goals for business continuity. It's a recovery point objective and a recovery time objective. RPO and RTO, both of these measure the availability of applications, and every business needs to have a story about RPO and RTO when it comes to disaster recovery. So RPO deals with how much data in time, how much data a business is afford to lose, right? And it is measured in time. For RTO is that when disaster hits, how long is going to take for the application to be available after disaster. Said differently in diagram. So in this diagram right here, you have RPO and RTO on both ends, and disaster hits in the middle. So that circle, green circle in the RPO line, that's when the successful sync happened. That's the last time the application actually was able to write to storage. And then from that, the actually it gets synced to the other side where if we need to recover data in the other side. So for example, if the last time the sync occurred at 10 a.m. and disaster happens at 10:03, then that 3 minutes, that's your RPO time. That's how much data actually in time is potentially lost. For the RTO, if the application after disaster starts running at 10:05, given the example of from 10 to 10:03 and then 10:05, then the 2 minutes is the time the actual application was down since disaster hit. Okay. Now, so regional DR is when you have a region, let's say US East, and then US West, and then the other region. You don't want to have both of them close together, right? So that when disaster hits in one region, doesn't take with it the other region, right? That's something very important. When it comes, then we also have Metro DR that I don't want to get into it in this talk, simply because Ceph pretty much handles that. When you have this, for example, 3 availability zones, in that case, if one availability zones goes down, then you still have the other 2 where you can access your application. But we'll focus on the regional DR. It's with regional DR, we have open cluster management, which deals with the application life cycle and cluster management. And then the OpenShift Data Foundation, which deals with data replication, handles data replication and storage management. And it is backed by Ceph, whose life cycle is managed by Rook. Okay, so how Rook enables data replication for DR? So RBD mirroring is a daemon that when it is when mirroring is enabled and this daemon is created, then data is synced from one cluster to the other cluster. So the first thing that Rook does is that it creates the RBD pool, enables mirroring, and then bootstrap the peers. and then finally it creates this daemon that does the data replication. With disaster recovery, with application disaster recovery, we will have both directions. Mirroring happens in both directions, from one cluster to the other, and then if you have other applications that are running in this cluster, then it moves to the other cluster as well. We do the mirroring the other way. So in this case right here, so at this point, Rook has enabled replication, mirroring between two clusters, and we need to use it, right? So volume replication is an operator. It's part of the Ceph CSI add-on that provides this capability. So for single volume replication, you will have two CRDs. You have the volume replication class that basically details the driver config parameters, and then we have the volume replication CR that actually deals with the actual volume that needs to be replicated from one cluster to the other. We also support volume group replication, and it is the same as the single volume replication. We have two CRs, the volume group class, volume group replication class, and the volume group replication CR that also now handles, instead of just a single volume, it handles multiple volumes. And that's for consistency groups. Okay, so now we need to build up from that point on, right? So we talked about Rook, and then how Rook enables mirroring between two clusters, then how that mirroring is used through the volume replication. Now we need to talk the application itself, how we can protect an application for disaster. So we have three major components that we depend on in this solution. We have, again, the open cluster management that handles application lifecycle and cluster management. We have the multi-cluster operator that sets up DR for Raman. And Raman is, again, it's also an open source. You can get to it. And it deals with, is the one that orchestrates the failover, failback, and setting up the protection as well. If we look at this diagram, right, what we have three clusters. We have one cluster in region 1, the other cluster in region 2, and we have the hub cluster, right? The hub cluster can be in region 1 or region 2, okay? All of these are Kubernetes clusters. All of these three are Kubernetes clusters. And what you see in this diagram also is that we have applications in both clusters. So this is not a active passive configuration. This is active configuration. You can have applications running in this cluster, application running in that cluster, and then when disaster hits, you can fail over either way. Okay. And again, in this diagram, we are showing that there is an initial deployment. We had applications running there, and we are deploying Kafka in this case. And Kafka was in this example, it has been deployed in cluster 1, region 1. The next slide shows that DR protection has been enabled. This is when the user creates a DR policy. Raman reconciles the DR policy and protects the application. As you can see, there is an asynchronous replication from cluster 1 to cluster 2. So we have a primary application running on cluster 1, right? And then on the secondary cluster, we have a volume. We have an image there that is basically act as secondary at that point, and you cannot really access it unless you force promote it, and that's when we do failover. So once disaster hits, then the user decides to fail over the application. At that point, we force promote the image on cluster 2, becomes the primary image, and we are at that point we are also expected to lose some data, right? Which is what we were talking about earlier. That's your RPO time. Because this is an async replication, you will lose some data from the time your last snapshot and sync occurred to the time disaster hits, right? And once the failover and the application is running on cluster 2, we go to cluster 1, clean up that cluster, and then reset the synchronization. And now we are, as you can see in this diagram, it is syncing from cluster 2 to cluster 1. Then we also have fallback, right? At some point, the user will decide that, okay, we need to fail back the application. In that case, the RPO is going to be 0. So the user would choose a maintenance window, 2 a.m. in the morning, for example, and it shuts down, the Raman is going to shut down the application, right, with the help of OCM, of course. Is going to shut down the application on cluster 2, and then fails back to cluster 1, and the application runs in cluster 1 again without losing any data, because this is not a failover, this is a fallback or relocation, as we call it, right? Anytime you want to also relocate the application from one cluster to another, you can also do that without losing any data, because the RPO for fallback or relocation is 0. Okay, we have two types of applications. We have managed applications, and we can handle managed applications, which is a declarative, from a declarative source like GitApps, right? And then discovered application. Application that, a legacy application, for example, that has been running in one cluster, right? And you want to protect that application. How do we do that, right? It's basically, it is discovered through ACM to OCM. It is discovered and made available to Raman for protection. The difference between managed application and discovered application is that discovered application, Raman and the DR solution basically only going to protect the persistent volumes, and because of the declarative nature of this application, OCM is going to deploy those artifacts when a failover occurs, right? For discovered application, however, all the resources that belongs to that application are backed up to an object store by Raman, right? So when a failover occurs, then all of those resources are restored as well. Not only the PVs, but those resources as well. Okay. We have a couple of tools for troubleshooting, and then the first one is actually for testing. You can have an environment, a Minikube environment, where you can have 3 clusters, and you can test all of this, right? Same way as it is real clusters, right? You deploy an application, and then you failover, relocate as well. And then we also have another tool, Raman CTL tool, which is used to validate clusters, to deploy applications, and so on and so forth. Both of these clusters are open source, written by Near Software, who is here with us, and they are there to try actually this solution. For more information about these, please see Nir. As I said, he's here. And then for any other questions, please see us. We'll be around. And yeah, thank you very much. That's all I have.
So I think we are past our time, but I want to make sure everyone has a little bit of time to maybe take a picture of this. Our booth hours at the Project Pavilion are tomorrow and Thursday. I think we can also make ourselves available in the hallway for a little bit if you have some follow-up questions here. But yeah, thank you, everyone.